Okay, guys, welcome to Let's Get to the Marks, going through the AS Chemistry Paper 1 Inorganic and Physical Chemistry walkthrough for 2024. This is the Paper 1. It's an hour and a half. You've got 9 questions, followed by Section B, which is the multiple choice. I suggest you pause the video, have a go at the question, then unpause and watch the explanation. So Q1, a student does a series of reactions with aqueous solutions of some potassium halides, P, Q, and R of equal conc. Each solution contains a different halide ion, chloride, bromide, iodide. The student adds 3 drops of bromine water to 3 drops of each aqueous solution of potassium halide. The student also adds 3 drops of the bromine water to 3 drops of water. Table 1 shows the student's observations. So we've got the color changes going on here. Obviously, bromine water's orange to start with, so it's actually only changed color with Q. Identify the halide present in Q, the halide ion. Give the ionic equation for the reaction that occurs when bromine water is added to Q. Why don't you pause the video now, have a go on some paper, then unpause and watch my explanation. Okay, guys, so think about it. If there has been a reaction, it's bromine water with a halide. So you've got to think about it. Which halogen is less reactive? I can't spell reactive, but which halogen is less reactive than bromine? What's the only one that bromine could displace? And also the brown color of the solution, which halogen or halide ion is brown when in aqueous solution? Hopefully you know it's iodide ions. So the brown is a sign that iodine has been formed, which means iodide ions have been displaced. So the answer to the first part is iodide ions have been displaced. Now we need to write the we need to write that. We need to write the ionic equation. So bromine plus iodide ions. Remember, it was a potassium iodide solution, but the potassium is a spectator ion as it doesn't change its physical state or its oxidation state. So here we go. We just need to balance this up. Let's put a 2 in front of the I minus and a 2 in front of the Br minus. And there we go. 2 lovely marks. Let's move on to 1.2. Explain in terms of oxidizing ability why the observations from these reactions do not allow the student to identify the halide ion present in P and in R. So did you notice the observation was that it stayed orange? If we flick back up, okay, and we look in the table, we can see that with with P and R, the bromine water stayed orange, so there wasn't a color change. So why is it that bromine couldn't react with P and R? Sorry, it reacted with Q, but not P and R. So why is it they can't identify it? Well, we can say, well, it stayed orange with P and R, in which case the bromine wasn't reactive enough to displace the halide ion. And what could be the possibility? Well, bromine is less reactive than chlorine, therefore bromine cannot displace chloride ions, so P and R could be chloride ions, but also bromine cannot displace bromide ions either, so it can't displace bromide ions. So we don't know if P and R are potassium chloride or potassium bromide. We don't know which is which because it would have stayed orange with both, so we can't decide that. And that will get you 2 marks. And then we can look on to the next part of the question, which says, okay, so if you can't decide whether P is potassium chloride or R is potassium chloride, what a further experiment is done. So the student does a second experiment to determine the halide ion in each of P and R, and this is for 1.3. The student adds a few drops of aqueous silver nitrate solution, that's AgNO3, AQ, to 2 centimeter cubed of each potassium halide. Now, the student observed with P and R a precipitate was formed, and it's going to be a white precipitate or a cream precipitate, but we're not given the colors. Describe a further chemical test that the student can complete on the precipitates to identify the halide ion present in P and the halide ion present in R. So I know that silver chloride is white and silver bromide is slightly cream, but that's pretty qualitative. So we're looking for a really accurate way to tell. And the further test that you should do is add dilute ammonia solution to both, and then add concentrated ammonia solution to both. And what we'll find is if we are dealing with silver chloride, the precipitate will dissolve in dilute ammonia, whereas silver bromide will not dissolve in dilute, but will dissolve in concentrated ammonia. And that's your answer for 3 marks. So add dilute ammonia solution to each, followed by concentrated ammonia solution is 1 mark. the silver chloride or the chloride ions, the precipitate containing chloride ions will dissolve in the dilute ammonia. The precipitate containing bromide ions will not dissolve in dilute ammonia, but will dissolve in concentrated ammonia. And just for your own information, you need to know, obviously, as you go further down the group, like iodine and astatine, iodide ions will not dissolve in dilute or concentrated ammonia. So if you had yellow silver iodide precipitate, which obviously contains iodide ions, they won't dissolve in either dilute or concentrated ammonia. Okay, and this will get you 3 lovely marks. Don't forget, if you're watching this video, to hit the like. It massively helps out the algorithm, get my videos out to students who are trying to pass their A-levels. Also, I will be going live every Monday for A-level chemistry and every Tuesday for A-level biology, where I will help students with any questions they have on the course. All right, let's move on to question 2. Okay, going through this A-level chemistry question. This one is about the elements in group 2, part of your A-level spec. So let's get into it. 2.1, explain why the third ionization energy of beryllium is much higher than the second ionization energy of beryllium, and it's worth 3 marks. So what we want to do is look up on the periodic table and find out beryllium's atomic number so that we can work out its electronic structure. So beryllium just has 4 protons, therefore equal to the number of electrons, 4 electrons. So we got 1s2 and 2s2. Now that's great when we do it like that, but when we show the box orbitals, we can really get into what is going on. So I'm going to show those arrows, and which each one represents an electron. Of course, they're spinning in opposite directions, hence 1 arrow up, 1 arrow down. That minimizes repulsion. So for the first ionization energy, I want to take away one of these electrons, right? So boom, taking that away. That's the first ionization energy. You're breaking into a brand new orbital, a completely filled orbital. And here we go. So that requires quite a bit of energy. Now the second electron doesn't require so much energy. Guess what? You're taking an electron from a partially filled orbital. So it's a little bit easier to remove an electron from a partially filled orbital. So we're going to zing that one out. And that was for the second ionization energy, okay? The second IE. Now look at the third IE. Now for the third IE, what are we doing? Well, a couple of things we need to know. We're breaking into a brand new energy level, and that's represented by 1. We're breaking into the first quantum level or shell or energy level. So that requires more energy when you break into a new energy level. So that's the main marking point. We're breaking into a new energy level. But what is it about that energy level? Well, that energy level is closer to the nucleus, and so feels the electrons in it feel a stronger attraction. Also, it's a completely filled orbital, so it's more stable. And also, there's no shielding. Look, there's no shielding here between the nucleus and these electrons. Whereas when we were removing these electrons, i.e. we were taking out the one for the second and the one for the first, these bad boys, they had the shielding between them and the nucleus of the first energy level. So we want to put all that down to get the mark. So the 3 main points are breaking into a new energy level, okay, which is closer to the nucleus. Now there isn't, so it's closer to the nucleus. So the electrons, are attracted more strongly, or they feel the stronger attraction. Whatever. We've expressed that, even though I can't spell or type. Attracted. There we go, or whatever. Okay, so that's like 2 marks. We're breaking into a new energy level. It's closer to the nucleus, more strongly attracted. The other things I want to cover are, I want to say, well, there's less shielding. So that's going to get me a mark as well. The fact that there's less shielding. Now we've removed that second energy level. No, you might want to actually say, if you wanted, I've left myself not a lot of room. I'd probably say when you're doing the second ionization energy, you're removing the electron from the second energy level. It's a partially filled orbital. and it has shielding. Whereas when you're taking an electron, the third ionization energy is removing an electron from a brand new shell that's closer to the nucleus, complete orbital, which is more stable, and there's less shielding. And as it's closer to the nucleus, more attraction, basically. So all of that, what I've said, I would whack in there as well. Kind of run out of room there with my explanation, but here we go. I'd put the whole lot down. That way you're guaranteed to get the 3 marks. If it's 3 points, I wouldn't just put 3 things down. I'd always try to put 4 or 5 things down, as long as they're correct scientifically. Okay. 2.2. Magnesium reacts slowly with cold water but rapidly with steam. Compare these reactions in terms of the products formed. You should identify one similarity and one difference between these reactions, and that's worth 2 marks. So you really have to know these reactions off by heart. If you don't know them off by heart, what are you doing? Get them on a revision card and memorize those. You can be just chilling out. Revision cards aren't perfect. You're not going to get an A star from revision cards alone, but these kind of revision tips, these are going to supplement your overall package. So if it's things like learning your group 2 equations, the best way to do that is to smash them onto a revision card and learn them like that. So we got like magnesium, when yeah, it's solid at room temperature, isn't it? If we add it to water when water is in the liquid phase, and you need to know this off by heart, guys. Just like all or most metal reactions with water, when we're looking at group 1 and group 2, and you did this in GCSE, you're going to make a metal hydroxide. Obviously, it's group 2, so there's going to be 2 hydroxide ions with it. Because each one of those is -1 and magnesium's group 2, so we'll be +2. And then what we're going to do, we're going to form hydrogen gas. You remember this from your alkali metal content in GCSE. And this is going to be AQ. Although magnesium hydroxide is only sparingly soluble, we can put AQ there, as some of it will dissolve. Now, it's not completely insoluble, magnesium hydroxide. So we've got magnesium plus water makes magnesium hydroxide and hydrogen gas. So let's have a look at what we make when it's with steam. So we're going to have magnesium solid plus water. The only thing you want to change here in the reactants is that the water must have a G next to it. Just spotted that's not balanced because I've got 2 hydroxides there, so I need 2 waters. Yeah, that's all balanced. Okay, so I'm going to do water, going to smash across. This time it doesn't make magnesium hydroxide, it makes magnesium oxide. You're going to see a white solid there. That's going to be insoluble, and it's going to produce hydrogen gas as well, which I'm running out of room. So we can spot here straight away, and that's balanced, that one, isn't it? Yeah, 1O, 2H's, 2H's, 1O. Yeah, yeah, yeah. That's completely balanced. Right, let's spot the similarity. Check it out. Okay, so let's put that similarity down. Both reactions release hydrogen gas. Now, imagine this question is just asking you to compare them and say what the difference is, what the similarities and the differences. Now, you could get one that's talking about observational similarities and observational differences, and this didn't. But if it was observational similarities, we could say, oh, you'd see bubbles in that one, or squeaky pop test, or whatever, some identifying feature of the hydrogen gas. Now, with the difference, you can see the difference as well. Let me just highlight that. Okay, let's highlight the difference. This one makes magnesium hydroxide solution, and this one makes magnesium oxide solid. So again, observationally, both magnesium hydroxide when solid and magnesium oxide are going to be white because they're group 1, 2, or 3 compounds, which are all white because they're not transition metals. However, you're going to see a larger amount of white solid with the magnesium oxide formation, whereas you've got water with the magnesium hydroxide forming a little bit of a colorless solution, as well as probably some white solid being seen there as well. Right, what's the main difference? All we have to do is say the difference here. The observations are quite difficult, so we're just going to say magnesium hydroxide. You don't have to do the formula. You could just write it formed with water, but with steam. MgO, magnesium oxide, is formed instead. Bosh. And that's going to get you the 2 marks there. All right, let me zing down, zing down, zing down, zing down. So zoom in a little bit. I've still got a cold. I've had this cold for weeks. 2.3, the reaction of calcium with water is a redox reaction. Explain in terms of oxidation states why this reaction involves both oxidation and reduction. So what we want to do here, guys, we want to write this one out. So this is typical. It's just a group two hydroxide reaction. This should be dead simple for you guys because you probably know your group one ones from GCSE. So H2O, which is a liquid, it's going to form calcium hydroxide like this. That's going to be aqueous-ish. You know, it's not, none of these are 100% soluble, but there we go. We're going to get hydrogen gas. So we just balance that up. We've got two H's there, two H's there. Oh, but I've got two H's there as well. So I need two of these and I've got two O's. That's all balanced. We just need the two there. Okay, so let's look at why this is a redox reaction. So you should know how to do this. Calcium is in its elemental state, so it has a zero oxidation state. If we take that through to here, calcium is now in a +2 state because it's a group 2 metal, and that means what has happened to it? It has lost two electrons. And what has happened if you've lost two electrons? Do you remember the little funky thing, oil rig? You probably learned that at GCSE as well. Oxidation is loss. So the calcium has been oxidized. So we can say, oh my days, check this out. Calcium has been oxidized. It lost two electrons. It got oxidized to calcium ions in the calcium hydroxide, and that's going to get us a mark. And then I also want to explain why there's reduction. We'll check out the hydrogen. The hydrogen has an oxidation state of +1. How do I know that? Oxygen is always -2, and there's two H's, and each one must be +1 to balance that -2 oxygen. Anywho, hydrogen is +1 there. But when you take hydrogen over here, hydrogen is now in its zero oxidation state. It doesn't have any ionic charge when it's in its elemental form. So what has happened? It's gone from +1 to 0. So um, H gained, oh my days, H gained an electron. What's gain of electrons? You know what the gain of electrons is, right? It's reduction. Reduction is gain. So we want to say hydrogen has been reduced. It gained an electron. Now, if we really want to get funky with it and over explain it, we can say it went from a +1 oxidation state, but the more I type, the more errors I make, to a zero oxidation state in elemental form. Okay, so from K, what the hell? There we go. I could have said the same whiffle waffle for that. I mean, you'll probably just get it for saying calcium has been oxidized, lost two electrons. But you could say calcium goes from 0 to +2, meaning it's lost two electrons, if you really wanted to get funky. And that's the end of the question. Don't forget sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. Okay, welcome to Let's Get to the Marks. Going through a question here on structure and bonding. Let's get into it. Define the term electronegativity. So electronegativity, if we look, for instance, at this bond, the carbon-chlorine bond, what happens? Well, you have a cloud of electrons here, and the chlorine atom is more electronegative and therefore has the ability to distort that cloud of electrons and withdraw it so that it is closer to the chlorine atom than it is to the carbon. At any 1 second, the electrons within that covalent bond are more likely to be closer to the chlorine atom than they are to the carbon. And so, yeah, that creates a polar bond. And how do we define that? We can say it is the ability of an atom to attract the pair of electrons within a covalent bond. Now, you could call, instead of saying a pair of electrons, you could say the electron density, or you could say the electron cloud around a covalent bond. So the ability of an atom to attract a pair of electrons, I think we could just say electron density. Some people use the term electron cloud. You'll have to check your mark scheme to see if electron cloud is allowed, but around a covalent bond. So the next question is explain why the carbon Cl bond is polar. And I kind of already went over that a little bit there. So the idea why the carbon Cl bond is polar is the chlorine atom has a higher electronegativity than the carbon atom. And the general rule for you when working out what atom is more electronegative is electronegative atoms that are electronegative are found on the right-hand side of the periodic table and up. So anything, if you imagine you have your periodic table, this is the crustiest drawing since humanity began of the periodic table, but you know it's got that kind of whatever shape. Okay, so anything on the right, electronegativity increases and going up here. So you're looking at the most electronegative atoms in the periodic table are up here, with fluorine being the most, followed by oxygen, which is in the group next door, or chlorine is just below fluorine. Chlorine's actually just also below oxygen, but it's still very electronegative. It's not electronegative enough to create hydrogen bonding, but it's still electronegative. You'll find fluorine, oxygen, and nitrogen are some of the most electronegative atoms in the periodic table, and they're found in the top right. So anything top right is very electronegative, and obviously opposite to that, these are electropositive, but we don't really use that term often in A level. So the chlorine atom has a higher electronegativity than the carbon atom. Um, so the chlorine atom um, draws the electron cloud or density, I should say, towards it. This makes so the electron density is not symmetrical, or it's unsymmetrical. And what do I mean by that? I mean the cloud of electrons in the bond are withdrawn this way, making this delta negative and that delta positive. Now, I know I've already scored 2 marks there, but I would also include that. So I'd be like the Cl atom becomes, and it's kind of like that. Oh my days, what's that? That's like an alpha radiation symbol. What the? Okay, becomes that. And what do we want to say about the carbon? The carbon atom becomes delta positive or slightly positive, we can say. Yeah, there we go. Slightly negative, slightly positive. I always think of that as a weird S for like slightly negative, slightly positive. All right, let's just zing that on there. Okay, that is definitely all of the marks. Oh, didn't put myself a tick there. So you could, they like the term electron density, so the ability of an atom to attract the electron density of a covalent bond towards it, or the ability of an atom to attract the electrons in a covalent bond. It doesn't have to be pair of electrons because it could be pairs if it was a double bond or whatever. But yeah, that wouldn't happen with a double bond because they would be symmetrical in their electron density. Okay, anywho, enough whiffle waffle. Let's move on. Right. 3.3. Although the CCl bond is polar, CCl4 is a non-polar molecule. Explain why. So yeah, think about the bonding in CCl. It's going to be CCl4. You're going to kind of have a tetrahedral. The bond angles are all going to be the same. So although the carbon is still, although the individual bond is I'm still not talking properly. The individual bond here is still polar, but they're exactly 90 degrees apart or whatever they are. What is it? What's the tetrahedral? 109.5. They're 109.5 away from, they're all equal distances. And this means the electron cloud is evenly spread. And so the dipoles cancel out. So what we want to say is, the bond angles are all the same. The electron cloud or electron density, I'm going to say the electron density is symmetrical, evenly spread. So the dipoles cancel out. It doesn't mean there aren't dipoles. There are dipoles, but they cancel out. So you get this situation which some students find confusing where CCl4 contains a polar bond, but it is non-polar. And so it has a polar bond, but all of those charges cancel out because it is a symmetrical molecule. So you could just say it's a symmetrical molecule. The dipoles cancel out, and that should get you the 2 marks, peeps. Right, let's zing on.
There are van der Waals forces between non-polar molecules. Explain what causes these forces. So let's take a look at, say, a non-polar molecule. Oh my gosh, is that the best I can do? Oxygen, right? Let's take a look at oxygen. Um, why why do we get um temporary dipole-dipole forces in oxygen? Well, at any 1 second, electrons are flipping. So at 1 second, the electrons might be in the bond, might be slightly closer to this oxygen, and then a second later, they might be slightly closer to that oxygen. And then a second later, they might be slightly closer to this oxygen, hence the bulge, no diddy, around this oxygen. And what this does is, this means that temporarily that becomes delta negative, and this oxygen atom becomes delta positive. And obviously one little oxygen molecule is not going to be on its lonesome. Okay, there's in 1 centimeter cubed, there's probably like a million oxygen molecules. So there'll be near enough another oxygen molecule close to it. And the repulsion of this negative, slightly negative oxygen atom will repel the electrons in this bond like that, because that is going to repel the electrons as far away from it as possible. And so this one becomes negative, this one becomes positive, and then what happens? That one's positive, so it's going to attract the electrons in this bond, because electrons are attracted to positive, so they're going to go down that end, and that one's going to become positive and negative. So the formation of a dipole here causes a dipole to form here, and we use the word induce. So we say formation of a dipole induces a dipole in this one, and then what happens is we get an attraction, which we show with a dotted line, a weak force of attraction set up between delta positive and delta negative, right? And that carries on like that. So that one's positive and this one is supposed to be negative. I should have drawn that there, but you get the ideas, peeps. So I just need to put that into words. So we're going to say the random, and so this is the first mark, the random movement of electrons causes one atom to be, yeah, delta negative. Could just say a dipole to form, couldn't I? But I'm being long. And the other to be delta positive. Um, and then I could, if I want to get real poncy, in a covalent bond, um, causing a dipole in the covalent bond. So this causes a dipole in the covalent bond. That's that bit that's formed there. Then we need to talk. So that's the first mark, and I've longed it out. We could have just said random movement of electrons causes a dipole. And then this induces a dipole in the neighboring covalent bond for the second mark. This induces a dipole in neighboring covalent bond. Now, that was all that waffle I was giving to you about this delta negative one repels the electrons away from it in the covalent bond, causing this part to become delta positive and this end to become delta negative. But you just solve all of that by just saying it induces the dipole in the neighboring bond. And then we say delta negative and delta positive between two molecules. There is a weak force of attraction. So a weak force of attraction forms between the, I'm going to write it this time, delta negative and delta positive between neighboring molecules. So what we're saying there, that is got to be distinct, is we're talking about the electrons within a bond here. The random movement of electrons causes a dipole to be formed. That induces another dipole, and that's the second mark, in the neighboring molecule. And then a force of attraction is created between the delta negative and delta positive between the adjacent molecules. Nice. And a final part to this question, barium reacts with oxygen to form barium oxide. Barium oxide has a high melting point and an ionic lattice structure similar to that of sodium chloride. Draw a 3D diagram to show how the particles are arranged in the barium oxide lattice. You should draw 8 particles, right? It says 3D, so I'm imagining if we check the mark scheme, you're not going to get well, for a start, this isn't going to be 8 particles, but you're not going to get the marks for that. That is a 2D structure, folks, and that has got some big old gap there. So I don't know, it's not much of a lattice structure, is it? So that's a 2D structure. So you might say to yourself, oh, let me try and 3D this out like this. And this is where, I mean, I got equivalent to a level 4 in GCSE art or a D grade, so that's not great, is it? Look, my atom's not even fully a circle, so you might think, oh, can I do it like this? I'm not sure they'll accept this because this starts to get a bit difficult, doesn't it, to show. They want 8 circles. I mean, that looks kind of 3D, right? And they're alternative, but I'm struggling now with getting 8, aren't I? So it's much better to do this instead, which is like 2 plus. You could write BA 2 plus if you want. And then maybe I should label these BA 2 plus. Yeah, we probably um, yeah, I probably need to put the elemental symbol in there. So I'm showing off to the examiner. I know that barium's in group 2 and it's 2 plus. So this is a much easier one to do because you can clearly see the only misconnection with this is this appears, this is an ionic bond. And when you draw these straight black lines, it's kind of like signaling a covalent bond. Sometimes I find is what it looks like. And then that is probably the worst lattice structure in history. But yeah, oh my days. That would just about get me 2 marks. I think I might need to put the symbols in here, guys. So if you can do, I'm not going to paint it out for you, but if you can do, show the examiner that you know barium is 2 plus. And if you can do, show the examiner that you know barium, oxygen is the 2 minus. So maybe I could just do it on one. Probably best to do it on all of them. Okay, that one I prefer because it's easier trying to do that. I don't know where I'd have to just continue it over here, maybe do 12 of them to show its 3D structure. You can't really see the ones that would be behind there. I could attempt to sort of draw them. I'm not sure the examiner would be happy about that. So yeah, I think this one here is the best way to show the lattice structure.
Okay, question 4. So a student is provided with separate unlabeled samples of 4 different solutions for analysis. The 4 solutions are known to be ammonium nitrate, potassium sulfate, sodium carbonate, and magnesium nitrate, but the student doesn't know which sample is which. Outline a series of test tube reactions that the student can use to identify each of these solutions. Include the expected observations and the ionic equations. So we've got 4 different solutions here, and we need to do 3 things for each. That's 12 things in total to get the 6 marks. So for each one, you need to say what you're going to, the name of the test tube reaction, the expected observation, and the ionic equation. Okay, so let's label these 1, 2, 3, 4, and we'll go through each one by one. So ammonium nitrate's the first one. So I want to test for the presence of ammonium ions. Hopefully you know the ammonium ion test. Why don't you grab a pen, paper, scribble it all down, and then you know the coup, unpause, and I'll go through it. So what you want to do for the ammonium nitrate is add sodium hydroxide. Obviously, you'd do this for all 4 test tubes, but what the positive result would be, you'd had whole damp red litmus paper at the neck of the test tube. And of course, that's going to release ammonia gas. And the ammonium gas is going to turn the damp red litmus paper, the ammonia gas, sorry, it's going to turn it blue, and that's going to identify which tube has the ammonium nitrate. So that reaction will only happen with one of the tubes. Now let's write out the equation for this. Of course, this is the positive result for ammonium ions. Let's write out the ionic equation. So we want to pay attention to the word damp here. The fact that it's damp means there's water there. That means we've got hydrogen ions and hydroxide ions available. And that means that what's going to happen is our ammonium ions are going to react. Our NH4 plus is going to, I should write a plus there on the NH4, made a mistake there, sorry, is going to react with the OH minus, and that's going to form ammonia and water. So sorry, that should have a little plus by the NH4. And now we're going to look at the second one, which is potassium sulfate. Now, for sulfate ions, normally you add an acid. You don't add sulfuric acid because it contains sulfate ions, so give you a positive result. You can add like hydrochloric acid or nitric acid, whatever. That's to get rid of any carbonate impurities. And then you follow that up by adding barium chloride solution, and you get a white precipitate, which confirms that we're dealing with a sulfate because barium, oh no, it doesn't form a barium chloride. Oh, it forms a barium sulfate precipitate, and that confirms that we're dealing with sulfate ions and the presence of potassium sulfate. Okay, and that's because Ba2 plus ions in the barium chloride solution react with the sulfate ions in the potassium sulfate solution. Remember, they're ions, they're all floating about, free to move. And so the barium and the sulfate ions get together to form barium, not barium chloride, you wally. They get together to form barium sulfate. What have I written now? I've written barium chloride. What an idiot. Yeah, sorry, they don't get together to form BaCl2. Of course, they form a white precipitate of barium sulfate. Okay, let's move on to the next one, which is sodium carbonate, part 3. So for sodium carbonate, we've got to think about what test tube reaction we could do. And for carbonates, you just add an acid, name the acid, generally nitric acid or hydrochloric acid will do. And once you've added that acid, we're going to see bubbles. The bubbles, I always write bubbles instead of effervescence. Effervescence is a better word, but I find it harder to spell. So you can see bubbles of carbon dioxide release. You're not going to get marks for saying, I see carbon dioxide, because you can't see carbon dioxide, it's invisible, but you can see the bubbles made by the carbon dioxide. And the ionic equation for this is carbonate ions, CO3 2 minus, plus 2 hydrogen ions, which will come from any acid, and they're going to release carbon dioxide and water. And that's your ionic equation. We should really say this confirms the presence of a carbonate, which tells us that we're dealing with sodium carbonate. Now, of course, sodium ions and potassium ions could be identified with flame tests, but this question is specifically about test tube reactions. Now we go to number 4. And number 4, we're going to add sodium hydroxide. And if you add that to each tube, when you add it to the magnesium nitrate, you're going to get a white precipitate of magnesium hydroxide. So the magnesium ions react with the OH minus ions. So you've got Mg2 plus 2 OH minus goes to MgOH2, very sparingly soluble, mostly insoluble, as you know from your hydroxides, group 2 stuff. And so you get a white precipitate, and that's how we identify that. Welcome to Let's Get to the Marks, going over shapes and molecules for AS Chemistry, also A-level chemistry. So we've got question 5 here. SF6 and SF3 plus have different shapes and different bond angles. Deduce the shape of FS6 and the shape of SF3 plus. State the bond angle in SF6 and state the bond angle in SF3 plus. Justify the bond angles by referring to electron pairs. So what we need to do here is we're going to get kind of 2 marks for working out the shape of both and stating the shape. You could draw the shape if you want, but they give the name of the shapes, state the bond angles in each, so another 2 marks, and then the 5th and 6th mark, I finally got it out, is for justifying the angles according to the bond pairs. So let's get onto it. Pause the video, have a go, grab some paper, grab a pen, give yourself a go, and then unpause and see if you can get as many marks as you can. Right, so let's go through the answers. SF6, right, and this is a bit long-winded, you don't need all of this, but I'll highlight the bits that you do need on the mark scheme. So sulfur is in group 6. This means it has 6 electrons in the outer shell, so there's 6 electrons around the central sulfur atom. It gains 6 more electrons from fluorine. That makes a total of 12 electrons. And if you do 12 divided by 2, you'll find out there's 6 bonded pairs of electrons. Well, 6 pairs of electrons. The fact that there's 6 bonds means all 12 electrons are involved in bonds. And if you have 6 pairs of electrons and all of them are involved in bonds, you're going to be this shape, and it's octahedral. And that goes for everything that has 6 pairs of electrons which are all bonded. You form this shape, octahedral, which is kind of like square plano with one above and one below the plane. So that's what it looks like. You just need to name it. It's octahedral. That's one of the marks. What we now need to do is justify it. So the fact that there are 6 bonded pairs, they try to minimize the repulsion between each of the pairs. The furthest they can move away from each other is 90 degrees, and every single bond has 90 degrees because there's equal repulsion between the bonded pairs. So what I should say, bonded pair repulsion is equal, and that's why we end up with 90 degrees. So that's really all of your marks for that. You could probably get 3 marks if you just left it there. You've named the shape, you've explained how many pairs of electrons there are, you've explained why they're equal, um, why they're trying to get away from each other, and why the bond angle is 90 is because they're equal. Now, sulfur normally has 6 electrons. I'm drawing this next one in pink. However, this has got a positive charge, right? Because it's SF3 plus. So it has a positive charge based over the whole molecule. This means there's 1 less electron around the sulfur. So there's only 5 electrons around the sulfur this time, and there are 3 bonds. 3 electrons from fluorine atoms. So technically you've got 5 electrons from sulfur, 3 from fluorine. That's 8 electrons divided by 2 to find out how many pairs you've got. So 8 divided by 2 is, even I can do that. That means there's 4 pairs of electrons. And we know that 3 are in bonds because we've got F3. So we know 3 of those pairs, 6 of those 8 electrons are bonded, which means we've got 2 electrons left over. There's 1 lone pair. Now you can just draw the dots, or you can draw a Mickey Mouse, a lone Mickey Mouse here if you want to. So when you have 4 pairs of electrons, but only 3 are bonded and 1 is lone, you form trigonal pyramidal. You can just call it pyramidal and you'll get the marks. Basically a pyramid without the top bit to make it tetrahedral. You should draw brackets around it in a positive charge if you're going to draw the shape. So that's going to get us marks. We've deduced the shape, we've deduced the name of the shape, and now we just need to state the bond angle and explain the bond angle for the last 2 marks. So trigonal pyramidal, the bond angle is going to be like 107.5, but it could be less. It could be like 105, 106. The main thing is that the lone pair, bonded pair repulsion is greater. So if you had 4 pairs of electrons, this would be 109 because it would be tetrahedral. Why is it? It still has 4 pairs of electrons, but if it was 4 bonded pairs, it would be 109. So let me do a quick diagram and show why it'd be 109. I'm not going to draw the 3D bonds, but basically, if you had 4 bonded pairs, you can see 2 bonded pair, 2 bonded pair has 109 degrees. But when you have lone pair, bonded pair, the repulsion is even greater. So what that does is the fluorine atom is repelled by even greater repulsion. So you only get a 107.5 degree bond angle. So you get a smaller bond angle when there's lone pair, bonded pair, because the repulsion is greater than bonded pair, bonded pair. And there we go.
Give the full electronic configuration of bromine. So if we look into the periodic table, bromine has, roughly speaking, people, the numbers 80 and 35. So it has 35 electrons. So, wow, we've got to do the full bad boy electronic configuration. So we've got to write out 35 electrons. That's big business. 1s2, 2s2, 2p6. It's got us up to 10. Then we enter the third energy level, 3s2, 3p6, 3p subshell. Now we're touching into the fourth and then back to the third. So we go 4s2, 3d10. And I need a quick add up to see how many we've got. 10, 20, 30. Got 5 more to whack in here. We've already done the 4s. What comes after s? It's the 4p. So we're looking at 4p, 5. And there we go. 35 electrons. A sample of bromine Br2 is analyzed in a mass spectrometer. The sample is ionized using electron impact ionization. Give an equation including state symbols for the process that occurs during the ionization of bromine. So we want to do the ionization in, the, so we're going to ionize bromine here. So we've got a bromine molecule. Bromine doesn't exist as atoms on its own. Hit by an electron. And then it goes into Br2 with a plus, still vaporized. And you've got the electron that smashed into the bromine and then the one that bounced off of the bromine. So technically, an electron cracked into the bromine and the electron bounced off, but in the process knocked another electron off. So that's what we're representing here. So we've got this electron that smashed into the bromine, knocking another electron off, so we're going to have 2e minus. That's just one way of representing it. The more common way is actually like this. Br2 gaseous arrow goes to Br2 plus gaseous and 1 electron. So you're not showing in this version, which is probably the more common, easiest way to write it. You're just imagining the electron impacting it. You're not having to show that electron that's whacked into it and come off. So you're just showing the electron that's being lost by the impact. Yeah, either of those will get you the mark. Okay. Bromine exists as two isotopes, bromine 79 and bromine 81, which exist in equal abundance, so 50% of each. Figure 1 shows an incomplete mass spectrum for this sample of bromine, 25%, 58. Complete the mass spectrum by adding a label to each axis and adding further peaks, what you would expect to see, 3 marks. So what have we got going up here? Well, we have we have percentage abundance. So that is my axes here on the y-axis, and on the x-axis we have the MZ ratio, or yeah, MZ ratio, MZ, yeah. Mass charge ratio, if you're wondering what that is the mass compared to the charge divided by the charge. And the charge on this is +1, so it's basically MZ is equivalent to the mass. Right, let's see. Well, you could have bromine 79, and that could bond up with bromine 79, and then they could lose an electron. So they would have a total mass of 158. Hence, this bar, 25% of all bromine exists as bromine 79, bromine 79. Then we could have bromine, what did we say the other one was? 81 and bromine 81. And so what that means is 25% of all bromine is going to exist as bromine 81 and 81. But then there's another combination that the bromine molecules can come together as, like bromine 79 and bromine 81, or we could have bromine 81 combining with bromine 79. And so that's double the amount of either of these. So 50% of all the bromine is going to have a mass of 160, because if you add 81 and 79, you make 160. If you add 81 and 81, you make 162, and 79 and 79, you make 158. So your marks here are really for labeling the axes and then getting the bars right and the right percentages for each of those bars. Okay. Final mark for this 6-mark question. 6.4, state how the detector enables the relative abundance of each ion to be determined. So what happens at the detector, just for those of you that are interested in these things, the detector is a negative plate with an ammeter attached. Okay, so there's my negative plate with an ammeter attached. Now you just imagine that bromine 158 has turned up. It's going to get there first because it's lighter. When it turns up, if there's 2 of them, what happens at the plate is electrons leave the negative plate and move towards these positive ions, because these ions are positive. And of course, the more of them you have, the more electrons are going to leave the negative plate. So the current that is formed at the negative plate is proportional to the abundance of that particular ion. Of course, bromine 160 or bromine 162, the heavier versions of these isotopes, are going to arrive later. So state how the detector enables the relative abundance of each ion to be determined. The size of the current generated at the negative plate is proportional to the abundance of the positive isotope. So basically, yeah, you get the idea. So for instance, we could muck around and say that's 2 amps. Well, if we double the abundance of this positive isotope, we then double the current. So, oh, it's gone up to 4 amps. Okay, lovely. All right, girls and guys.
Okay, some runners use tablets to help muscle recovery after long races. These tablets contain magnesium oxide. A student wants to find the percentage of by mass of magnesium oxide in the tablets. MgO reacts with hydrochloric acid to form magnesium chloride. We've got a reaction here, and then we've got a second reaction in an experiment. The student adds excess hydrochloric acid to some tablets. The student then does a titration using sodium hydroxide to find out how much of the excess acid is left. The student follows this method. Place a beaker on a balance and record the mass. Add 6 tablets to the beaker and record the mass. Add 25 centimeter cubed to 2 mole per decimeter hydrochloric acid to the beaker and stir until all the magnesium oxide has reacted. So we're reacting all the magnesium oxide. It's the hydrochloric acid that's in excess. So make the mixture up to 250 centimeter cube with dilute water in a volumetric flask. Transfer 25 centimeters of this diluted mixture to a conical flask. Add 3 drops of indicator. Add 0.09 mole per decimeter sodium hydroxide solution from a burette until the indicator changes color. Here are the results. Mean mass of the tablet 2.14, mean titer 20.38. Each reading from the balance has an uncertainty of 0.005. Calculate the percentage uncertainty. So what we need to appreciate here, folks, is that the balance was used twice. Once to record the glass beaker and the mass of the tablets, and just the glass beaker on its own, and then the beaker with the 6 tablets. So they got 2 readings. So when you calculate the uncertainty, you need to take into account the amount of readings to do the measurement. Now the measurement is 2.14 grams, and we're going to do the uncertainty times the amount of readings over the measurement. So 0.005 times 2 over 2.14 in the calculator times 100s, and we will get the percentage uncertainty. And I believe that is 0.46 7%. There we go. Leave a note in the comments if I've made a mistake. I've made mistakes before, by the way. Okay, so that will get you 1 mark, and that's calculating the uncertainty. Now it says calculate the amount in moles of hydrochloric acid that was added to the tablets in step 3. So notice there are 2 equations here, and that's always a sign we're doing a back titration. But in the first equation, they added 25 centimeter cubed of 2 mole per decimeter hydrochloric acid to the beaker, and this was the excess. This was the initial or original moles of hydrochloric acid, and you just need to do C times V, and that's the volume is 25. Remember to turn it to decimeters, divide by 1,000, times by the conc, which is 2, and that's going to give us 0.05 HCl moles, or 0.0500 if you want to be fancy pantsy. All right, and that's going to get you another mark. Now we got, so that's 2 of the marks for this question 7. Now we've got a big fat 6 marker. So make sure you pause the video and have a go and then watch my walkthrough. Use the answer to question 7.2, that's the 0.05 mole we just did, and the information given to calculate the percentage by mass of magnesium oxide in the tablets. We want to know how much MgO is in the tablets. I'm going to do the equation and the answer up here, not down below. So, because I've got the 2 equations here. Now, when you get 2 equations like this and they add something into excess, you know it's a back titration. So we've already worked out the original moles of HCl, and that's 0.05, I guess 0.0500, but 0.05. We now know that they then took the leftover HCl, which we don't know yet, and they diluted it down. They took a tenth, right? They put the mixture up to 250 and then just took 1/10. So we're going to have to multiply our moles by 10 at some point, and they always do this. And now we've got the conc for sodium hydroxide, 0.09, and we have the mean titer, which was sodium hydroxide being titrated with the acid. So let's work out how much sodium hydroxide was used with the leftover HCl. So, and it's a 1-to-1 reaction. So if we calculate this, the moles of sodium hydroxide, you also have the moles of the HCl. So let's get to it. So 0.09 is the conc of the NaOH. Oh, I haven't got space to write this over here. Hold on. I'm going to write out the volume. So it's 20.38 divided by 1,000, right? You could just write 0.02038 if you prefer, but I'm just going to write it as 20.38 divided by 1,000. That's the volume because we're going from centimeter to decimeter. Times it by the conc, and this is the sodium hydroxide concentration we're calculating now. Sorry, not conc, moles, which is 1.83 times 10 to the minus 3. Now, what do we want to do next? We want to realize that that is only that's one-to-one reaction. So that's the hydrochloric acid moles, but we need to times it by 10, which gives us 1.83 times 10 to the minus 2. Okay, because we only use the 10th and we know it's one-to-one. So we now know how many leftover moles of HCl there were after the reaction. So our excess leftover moles of HCl was 0.0183. So we titrated 0.00183 moles of NaOH, but then we times it by 10 to go back to the original HCl there. Right, now we want to find out how much HCl reacted in the first equation with the magnesium hydroxide. So we're going to take the original HCl, which is 0.05, take away the excess leftover HCl that we found out how much that was with the sodium hydroxide. We find out that actually 0.0317 moles of HCl reacted in the first equation up there. Now, we can work out the moles of magnesium oxide from that because the ratio is 2 to 1. So we need to divide 0.0317 by 2, and this will get us the original moles of magnesium oxide. So 0.0317 divided by 2, we get 0.01585 moles of MgO. Now I need to convert that into mass because we want to work out the percentage of MgO mass in the total mass of the 2.14. So I'm going to do mass, I'm going to do Mr times N. The Mr of magnesium oxide is 24.3 for magnesium, use your periodic table, and 16 for oxygen, so it's 40.3, times 40.3 by 0.01585, which was my moles of magnesium oxide. And we're going to get 0.6387, something, you could round it, but something along those lines, 0.64, whatever, grams of magnesium oxide. I now need to work out what percentage of the 2.14 was magnesium oxide. So I take my 0.6387 and I divide it by 2.14 grams, which is the total mass. So it's the mass of the MgO over the mass of the whole tablet and times 100. And so we'd be up to 5 marks right now, and we just need to do this to get the 6th mark. There we go. And what is that going to equal? Oh no, I smashed that in the calculator. That is going to equal 29.848%. What do we want to round that to? We could leave it as 29.8. Right, if we just go to 3 sig fig, 29.8. If you want to go to 2 decimal places, I guess it would be 29.85 because the 8's bigger than the 4. So yeah, there we go. All right, guys, let's move on to question 8. Okay, guys, on to question 8. Don't forget to hit the like. I know I say it a lot, it might annoy you, but like these walkthroughs are a lot of work, dude, and I don't really get paid much for this kind of stuff. So, this question is about silver nitrate. Define the standard enthalpy of formation. So, really, this one is just a standard asking you the question. When you get on to A2, so it's the enthalpy change when 1 mole of a compound is formed from its elements under standard conditions, okay? But the application of this comes up a lot in A2, and the application of this is to remember that it's 1 mole of the compound. It don't matter how many moles you have of the elements, okay? So it's always 1 mole of the thing you're making is what the number is for. It doesn't matter whether you need to use 2 moles of elements. It's always just about the 1 mole of the compound. Okay. And that will make itself clear when you do application questions in A2 when you're talking about Born-Haber cycles and things like that. Okay, silver nitrate is formed when silver nitrate 5 is formed when silver nitrate 3 undergoes thermal decomposition. The standard enthalpy of formation of silver nitrate is -123. The standard enthalpy of formation of nitrogen oxide gas is 90.4. The overall enthalpy change for this reaction is +56.2. Determine the standard enthalpy of the formation of the AgNO2. So we're going to write the equation out here, and I'm going to put the enthalpy change just above the arrow, which is plus 56.2. And we're going to do a Hess's law cycle. Now, the way I do it, a lot of people don't do it like this, but I do it with the big arrow that goes round. So that equals 56.2, this reaction at the top. And we've been given the enthalpy of formation. Now, when you do a Hess's cycle, you're going to have arrows going up when it's formation. If it's combustion, you're going to draw two big arrows going down, one from the reactants and products. So my arrow to the reactant is going up, and we actually don't know the enthalpy of formation of AgNO2. And my arrow to the products is also going up because we're forming it from the elements. So at the bottom, I could write silver, I could write nitrogen, I could write oxygen. I haven't bothered, but I could do that. So the arrow going up on the right hand side is plus 90.4, and that is for the formation of NO. And then I've got the formation of the AgNO3, which is minus 123. We don't need to do the formation of Ag because it would be in its elemental form, so it'd be 0. So it's being Ag formed from its elements is Ag is 0, right? I draw a big red arrow going around. Now I don't know the AgNO2 formation, so I'm leaving that as 2 times X because there's a coefficient of a 2, so 2 lots of X. I've drawn the big red arrow going round. You always do this going anti-clockwise, and now I'm going to write this out as an equation. So 2X plus minus 123 plus 90.4 equals 56.2. And that's the way we write this out. So all I want to do, where can I move this? I'm going to move this up here. Okay, now we're going to rearrange this equation. Don't forget at this point, it was a good idea at the start of each of these to pause the video and have a go. Anywho, what we're going to do now, in order to simplify this equation and then rearrange it to find x, so I'll go through how to do that. Well, first of all, I've got the minus 123 and the plus 90.4. So what you're going to do is you're going to go 2x, you're going to take the minus 123 and add it to the 90.4. They're the same kind of quantities. So we're going to get minus 32.6 equals 56. Now I want to add 32.6 to each side to get rid of that. So I'm going to add 32.6 to each side. And that's going to leave me with 2x is equal to, what is 56 plus 32.6? What is that? 88.6? Something like that. So 2x is equal to 88.8. Sorry. Something along those lines. And yes, so now what we're going to do is 88.8 and divide it by 2. We're going to find out that x is equal to 44.4. There we go. But is it a plus or is it a minus? And that's where we go back over here and we look at the red arrow that I drew going round. Because the red arrow that's anti-clockwise that goes around over here clashes with this formation arrow going up, you reverse the sign for the 2x. So instead of it being 2 times 44.4, it's 2 times minus 44.4, and we would have reversed that. So yeah, the answer is minus 44.4. Okay, let's zing down. So 8.3 suggests why the enthalpy change for the thermal decomposition of solid silver nitrate 3 is difficult to determine experimentally. Now, the main answer here, the main thing to think about, this is a thermal decomposition reaction, so you're adding heat in. So it's really hard to find out the enthalpy change when you're heating it, right? How much heat are you putting in as related to how much heat is being absorbed and that kind of stuff. So to work out the temperature change for this reaction accurately is pretty difficult because it's a thermal decomposition reaction, and so it requires heating to get in order for the reaction to happen. So they're pretty difficult to work out experimentally. Okay. Okay, you can read yourself through this next one. We've got a little method here, and it's for the reaction of silver nitrate with sodium chloride to form the silver chloride precipitate and sodium nitrate. They've got this method, and there's 3 inaccuracies, and we want to look for improvements. So just read the method carefully and look for improvements. There's probably 7 or 8 improvements you could do with this method. They'll be on the mark scheme. I'm just going to go through 3 of them. As I'm tired, it's near the end of the paper. I'm going to give you the 3 that stand out as the most obvious to me. So describe how the student could improve 3 aspects of the method to obtain more accurate results. So let's have a little butchers. Measure out 50 centimeter cube using a measuring cylinder. Right, in chemistry, measuring cylinders are not as accurate as what bit of equipment? So using a measuring cylinder, what would you use instead? A pipette, although we're doing A level. So let's delete that. Let's write volumetric pipette. So much more accurate. You could use a burette as well. That's very accurate, but that's pretty difficult to use. Much easier to use a volumetric pipette. So that would be the first inaccuracy and the improvement. Next thing they did, check it out, line 2, they used a glass beaker. When you're doing the enthalpy change experiments, you shouldn't use glass. It's not a very good insulator, is it? So what's a better thing to use instead of a glass beaker? A polystyrene cup. But of course, you could use a glass beaker surrounded with cotton wool or an insulating material. So you could say that as well. And that's going to reduce heat loss. Now, they don't want the explanation, okay? They don't want you to say reduces heat loss. And they don't want you to say polystyrene cuppo. I don't know what's wrong with me. Anyway, yeah. But so really, glass beaker is inaccurate because of heat loss. Insulator, polystyrene cup reduces the heat loss. Right, let's look for a third one. So I'm going to go down here to weigh out 2 grams of the solid, blah, 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 weighing boat, reweigh the weighing boat. That's good. They've done that. Add a lid to, oh, what haven't they done? So they've added the solid. They've added the sodium, silver nitrate solution, the sodium chloride solid. They've added straight to the silver nitrate, and the reaction's going to start, and then they're taking the temperature. They should have taken the initial temperature of the silver nitrate solution before adding the sodium chloride solid. So how do they know what the starting temperature is so that they can record the temperature change? So that's pretty inaccurate. So they did not record the initial starting temp. And remember, you record several initial starting temps here, and they really should record the maximum temperature, and then they should extrapolate back, which they didn't say. So you could have gone on about the old extrapolating back to the point of addition to work out the maximum temperature change. But peeps, I'm just going to say they didn't record the initial starting temp, and they should have done several readings of an initial starting temp of the solution before adding the solid. And there we go, 6 marks. Boom, boom. Let's get on to question 9. Welcome to Let's Get to the Marks. I'm going through a question about redox reactions, good for AS chemistry or A-level chemistry. Let's get into it. 9.1, state in terms of electrons the meaning of the term oxidizing agent. What you're looking at here is, what does it mean to be an oxidizing agent? Well, an oxidizing agent is something that causes another atom to lose electrons. So itself is getting reduced. An oxidizing agent itself gets reduced. Well, what does that mean? That means that it must be taking on those electrons. So what we can say about an oxidizing agent is that it is an electron, acceptor. Now, something when looking at the mark scheme to this, do not say it can accept a pair of electrons, because that doesn't make you an oxidizing agent. You might only need to take one electron and you're an oxidizing agent. So chlorine is an oxidizing agent, or certain other things are oxidizing agents, and they may only need to accept one electron. So yeah, there we go. Give a half equation to show the oxidation of copper to copper-2 ions. Let's get zinging into that. Let's mash this one up. So we know we got copper, the formula is Cu. With these half equations, good to draw an arrow, and then it goes to copper-2 ions. So we know they're going to Cu2 plus. We don't need to show state symbols, but if we did, we're going to get aqueous going on here. But what has it lost? It's lost 2 electrons. So that is literally the equation. Simple as that. Beautiful. Right. I've got a bit of a big space there, but ho-hum. Given a half equation to show the reduction of NO3 minus ions, this is always key in these redox reactions, in acidic solution to NO2. This should give you clues. So NO3 minus. Now we've been told it's acidic solution. That normally means that you have hydrogen ions knocking about. And I'm going to draw a little arrow, and we know that it's going to go to NO2. Now there's oxygen here, and the oxygen and the hydrogen in acidic solution is going to mean that we get water as well. And now we just need to balance it. So I've got 3 oxygens. There's 2 there, 1 there. It's looking all groovy, looking all balanced. But where do I get this extra hydrogen for the water molecule? There must be 2 hydrogens. Now, when I do that, this is electrically imbalanced because there's a -1 charge here and there's 2 times plus. There's an overall plus charge. I want to neutralize this charge because unless there's a charge on the right, and there isn't, it's neutral. I need both sides of the arrow to be equal in electric charge. And so what I'm going to do in order to whoopsie, in order to get rid of that plus sign, what I'm going to do is I'm going to add 1 electron like that. And so now E minus plus the NO3 minus is cancelled out by the 2H plus. We're electrically neutral on both sides. And so that is going to give me nice marks. Now we want to do an overall equation. And when you're doing the overall equation, what you want to pay attention to is the number of electrons. So I've got 1 electron there and I've got 2 electrons there. And that means I want to combine all the reactants down here with the reactants up there. And then I want to combine all the products up here with the products there, put them together in the overall equation. But what I have to do is make sure that they balance out. And so I need to multiply this by 2 so that my electrons here are also 2 and that cancels out. So always use the electrons in half equations to multiply and then cancel out. So I'm going to have in my final equation, I'm going to have 1 copper. I'm going to plus, remember I had to multiply everything down here by 2 to make the electrons cancel. So I'm going to make 2 NO3 minus. If I want, I can write, I then had to double the hydrogen ions, so that's going to be 4H plus. We doubled everything on the bottom row. Plus, I could double the electrons if we really want to show the electrons. I'm going to put 2E minus there. Then I want to write Cu2 plus. I only need 1 of those because we didn't double the top. And I want to write 2 lots of NO2 because we doubled everything down here. And I want to write 2 lots of H2O because we doubled everything down here. And also I got 2 electrons plus 2E minus. But guess what? The electrons actually cancel on both sides. So really we should take our rubber and we should get rid of these electrons because they are cancelling out on both sides. And sometimes check your hydrogens. Sometimes you cancel some of the hydrogens out. In this case, I've got 4 H's in the water, so I need my 4 hydrogen ions here. And there we go. That's the overall equation. So lovely jubbly. And here we go, guys. That was just a quick little video on redox reactions. Sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. I'll see you guys on the next vid.
You're still here? It's over.
Welcome to Let's Get to the Marks. Big shout out to Nicola Korzek and Ash Ford, the members. Thanks for supporting the channel. What I'm doing is going through the AS Chemistry MCQ questions, the latest ones by AQA for the AS syllabus. So don't forget, you need to colour in the little circle. Don't do any other method. They'll ignore it if you put a tick or if you put a cross. If you've made a mistake and you want to let the examiner know you've made a mistake, put a neat cross through your little black circle and then put your black circle in one of the other answers. All right, let's get into it. Let's get into smashing through these. Don't forget to pause the video, have a go on some scrap paper, and then unpause and watch the walkthrough. Okay, so let's get on with the first question. Question 10, what is the percentage atom economy for the formation of sodium nitrate in the reaction between sodium carbonate and nitric acid? So we're really looking at the atom economy. Sodium nitrate here is the useful product. I've underlined it in purple. It's the one with the 2 NaO3. So we want to do 2 times NaO3. Remember, Na is 23, the Mr or Ar. Nitrogen's 14, oxygen 16. 3 times 16 is 48. Whack that all together. And then what we're going to do, we want to divide that by the total products. So the only useful product here is the sodium nitrate because we're doing the atom economy for that. So we don't include the water and carbon dioxide on top. And underneath we put the sodium nitrate and the water and the carbon dioxide. And we remember the coefficient, the 2 times. So you put the total underneath. So Na is 23 plus 14, that's 37, plus 48, that is 85, times 2 is 170. So at the top we've got 170, and then at the bottom we've got 170 again, but we're doing plus 18 and plus 44, or is it 46 for the carbon dioxide? Let's see, carbon is 12, 44 because oxygen 16 each, 2 is 32. Right, so 170 plus 18 plus 44. So we're going to end up with 170 over that times 100, and you get something like 73.275%. Obviously, the 5 is greater, so you'd round that up to 8 if you were putting it to 2 decimals. But we're going to go 3 sig in A level, so we're going to round it up to 73.3%, and the correct answer here is D. All right, let's zing to the next question. So, which of these involves the formation of a dative covalent bond? So, just a quick reminder, a dative covalent bond is where both shared pair of electrons come from just one atom in the covalent bond. So, let's check this out here. I've got PCl3, it's going to join with a chlorine molecule. And what you're going to end up with here is each of the phosphorus is in group 5, so it's got 2 spare electrons. Each one of those electrons can be donated to share with the outer shell of chlorine. That's not a dative covalent bond. They just form normal covalent bonds. And then here we've got ions. We've got a sodium ion, a hydride ion. They're not going to get together like that. That's going to be an ionic bond. Again, we got some more ionic bonding going on here, but you can still have dative covalent bonding. But let's check it out. I've got my chlorine atoms, part of the chlorine molecule, and they're going to both take an electron from the outer shell of the magnesium and going to end up as 2 negative chloride ions. And the magnesium, of course, can end up a +2 metal ion. But let's try out this BH3. So we've got boron, which is in group 3, so it only has 3 electrons in the outer shell. So those electrons are already taken up by being paired with hydrogen atoms. But of course, this means there is room to expand, or it's got room to accept electrons, and a hydride ion has a pair of electrons, and both of those electrons are donated to the boron like that. And that is going to be the answer to 11 is D. So 12, the table shows some results from a titration. We've got the rough titration, you never look at those in a calculation, and then titra 1, titra 2, we've got the initial and final readings for each. Which is the correct mean titra? So let's look for concordant results. The concordant results here are going to be 25.9 and 26 because they are within 0.1 of each other. 26.20 is like 0.2 out, so it's not included. So we're going to do 25.9 plus 26 divided by 2, and that's going to give us 25.95 centimeter cubed. So the answer is A for 12. Let's move on. Part 13, or question 13, coming up next. So, question 13, which species is never formed during the reactions of chlorine with water? So we've got A, chloride ions, B, chlorate 1 ion, C, hydrogen, or D, oxygen. Yeah, you can probably guess which one of these doesn't get formed, but let's go through the equations that you should know off by heart from group 7. And there are 2 reactions of chlorine with water you have to know off by heart. So this first one, we've got chlorine reacting with H2O, and we're going to form some hydrogen ions, some chloride ions, and some chlorate ions, chlorate 1 ions. Now, this can answer us, the first 2 answer us for A and B. Are they true? Can you get chloride ions when chlorine reacts with water? Well, yes, look, it's right there, one of the products. Can you get chlorate 1 ions? Yes, it's right here. Oxygen has a -2 oxidation state, so chlorine in this situation is +1. That means it's chlorate 1. So yes, you can get chlorate 1 ions formed. Let's look at the other reaction that water undergoes. So we've got some chlorine reacting with H2O here, and it also is going to form some hydrogen ions. We're also going to get some chloride ions, and this time we're going to get oxygen gas formed. And so D is also formed. So the answer here is going to be hydrogen is not formed because oxygen can be formed. But hydrogen, of course, you might get mistaken and think, but there's H plus there, but those are hydrogen ions, completely different than hydrogen gas, which is in its molecular form. So no, hydrogen gas does not get formed. Pretty good as well, because you don't want them to put chlorine in the swimming pool and it to blow up when you go for a nice little swim. Okay, question 14. Which statement is correct? Calcium oxide is used to remove sulfur dioxide from flue gases. Calcium has a larger atomic radius than barium. Magnesium has a lower electronegativity than barium. Magnesium is used to oxidize titanium 4 chloride in the extraction of titanium. First of all, if we look at calcium, as we go down group 2, you could look at your periodic table. Barium is below calcium in group 2, and as we go down the metal groups, the atomic radii get bigger, so it's not true. Calcium does not have a larger atomic radius than barium. Then we can look at magnesium. Does it have a lower electronegativity than barium? Electronegativity actually decreases going down the group. Why does it decrease going down the group? They become more electropositive. Barium has the outer electrons, the two outer electrons are further from the outer shell than in magnesium. They're more likely to get lost. It's more likely to become positive. Electronegativity is the ability of the atom to withdraw or draw electrons toward them in a covalent bond. And barium does not have that ability to draw electrons towards it. So it's more electropositive. Neither of them are electronegative, but magnesium's definitely not as electronegative as barium. So magnesium is used to oxidize titanium chloride in the extraction of titanium. Let's write the equation out. TiCl4, you have to know this equation off by heart, it's part of your group 2. Magnesium, and let's check the oxidation states and see, does the titanium chloride get oxidized? Well, titanium is +4 in titanium chloride and it's 0 in its elemental state. What's happened to go from +4 to 0? It's gained 4 electrons. That is reduction. The titanium chloride has been reduced, not oxidized. So the magnesium itself is oxidized to a +2 state from a 0 state initially. So actually, no, the magnesium is being a reducing agent here and is reducing the titanium. So that's incorrect. And of course, calcium oxide, along with various other substances, can be used to neutralize the acidic gas, sulfur dioxide, from flue gases, and that prevents acid rain. Okay, let's go down to question 15. Which element has the lowest melting point? Now, the general trend for melting points as we go down group 1, 2, and 3 is the general trend is that the melting points get lower. Melting point decreases down the group. Why is that? Well, think about it. The the atoms get bigger, or the atomic radii increases going down groups. And what that means is the metallic bonds are weaker because they're not as they don't have such a high charge density as you go down the group. But we do know that group 2 has a stronger positive charge and so forms stronger metallic bonds between the positive metal ion and the delocalized electrons. So generally group 2 will have higher melting points than group 1. Group 1 are going to have the lowest melting points there, and potassium is going to be lower than sodium because it's further down and it has a less or a lower charge density, essentially, so it doesn't form as strong metallic bonds as sodium. Hokey cokey then. Right, 16. Which row correctly shows the general trends and properties across period 3? Okay, so as you go across any period, the nuclear charge increases because we have an increasing number of protons. And if the nuclear charge increases, it means the outer electrons are being held more strongly, stronger electrostatic force between the nuclear charge and the outer shell electrons. And this means the atomic radius decreases slightly, and also it becomes harder to remove the first electron. So the first ionization energy increases. And here we go. Remember, there's no extra shielding as well. You're adding electrons to the same shell, so you haven't got that pushing the outer electrons out either. So all reasons for why the atomic radius decreases and the first IE goes up. Okay, ammonia is oxidized as shown. NH3 plus oxygen goes to water and nitrogen monoxide, which are the whole number values for W, X, Y, and Z. So I would start here by going, well, let me crack a 2 in front of NH3 because I need to make that 3 an even number because I've got 2 hydrogens on the right, and then you can just balance it up like so. And then what we end up with is finding that we have 3 oxygens for the 3 waters, and we have 2 oxygens in the 2 nitrogen monoxides. That's 5 oxygens. So if I want to balance that, I've got to go back to the left and put 2.5 oxygen in. But then we read the question, it says whole number values. So I need to multiply everything in there by 2. So I'm going to end up with 4, 5, 6, 4. And that is C is the correct answer. There we go. Right, we're nearly getting to the end now, folks. Stay with it, stay with it, stay with it, stay on it. Let's go. Question 18. What is the empirical formula of an oxide of chlorine that contains 42.5% by mass of chlorine? So we've only been given the percentage of one of them. That means you can work out the other one. Pretty easy, right? We've been given oxygen and chlorine in this molecule. We know that the chlorine is 42.5%. So what does that make the oxygen? That makes the oxygen 100% minus 42.5. You can probably do that in your head. That's 58? No, 57.5%. Ooh. Now, what do we do with empirical formula? Well, when you're given percentage instead of mass, we just pretend that the percentage is grams. So we just do 42.5%, pretend it's grams, divide it by the AR to kind of get the moles. So you kind of do 42.5 over 35.5. That should equal 1.2. And then
Um,
57.5 over 16, which is the AR of oxygen, that should equal 3.5-ish, or 3.49. I think instead of 1.2, it was 1.19, but I've rounded here. Divide by the smallest for both to get the simplest ratio. You get 1 to 3. That's ClO3. Boom! B's the correct answer. Which of these solid halides does not reduce concentrated sulfuric acid? So here you've got to know about your group 7 reducing ability. Now, if you look going down the group, you've got fluorine, chlorine, bromine, iodine, astatine, right? As we go down the group, they get bigger, these ions, and less able to hold on that outer electron. So the smaller the ion, the closer that outer electron is to the nucleus and the less able it is to give it away. So out of all of these, fluorine, chlorine, bromine and iodine, astatine is probably the easiest, but iodine is going to be a lot easier to remove an electron off than chlorine or fluorine because they're a lot smaller. They've got the electrons closer to the positive nuclear charge, harder to get rid of the electron. So iodine naturally is better at reducing things. Remember, reduction is gain. Iodine's better at giving away that electron, being oxidized itself, and giving an electron to something else, which is reduction. So iodine is the stronger reducing agent. Chloride is actually a rubbish reducing agent because it doesn't want to give away its electron. It's gained that outer electron to form a stable octet, or whatever you want to say, a full octet, and it doesn't want to give that electron away. It's quite small, the electron's quite close to the nucleus, so sodium chloride is not going to undergo redox, and it's because chloride ions are not strong enough reducing agents. However, bromide do redox, iodide ions do even further redox. Okay, 20, last question. Samples of 4 different substances are analysed using the time of flight TOF mass spectrometry. In each case, the samples are ionised to form ions with a single positive charge. The ions are accelerated to the same kinetic energy. So which sample gives the ions the shortest time of flight? So the factor here is they've got the same kinetic energy. It's going to be the deciding factor is their mass as to which one is going to be travelling the fastest. So we're looking for an ion with the smallest mass. That is going to get to it's got the same kinetic energy, smallest mass. It's going to end up getting to the detector the fastest. Okay, so we're looking for the lightest ion. That's going to get to the detector the fastest, or the ion with the least mass. Let's not forget that electron impact doesn't increase the mass number, but electrospray adds a hydrogen ion from the solvent when it's passed over the kind of high voltage nozzle. Okay, so what have we got here? We've got SC45. So that's going to be SC45 plus because it's electron impact. Then we've got B is propane. So propane has an MR of 44, but it's electrospray. So it's going to have a hydrogen ion or a positive proton, sorry, added. So it's also going to be 45. I now know it's neither of these because they're the same, so they can't be the answer. A sample of CH3CH2OH, so that's 15 plus 14 is 29, 39, 46 is the MR for that, and it's electrospray, so it has one added, so that's going to be 47 is the mass number for that. So that is the heaviest one. And a sample of CO2, which is 44, that is ionized using electron impact, that's going to be the quickest. D is going to be the fastest to get there. Okay, moving on, a couple of questions to go and then we're done. So what I need to do is write the configuration out here. Now you can go to the periodic table and check out the atomic numbers. Phosphorus has the atomic number 15, so it's going to be 1s2, 2s2, 2p6, 3s2, 3p3. That means there's 3 unpaired electrons because the 3p orbital is the 3p subshell. Sorry, is made up of 3 orbitals. Each one can only hold 1 electron. So they're going to be 3 unpaired electrons. Let's check out vanadium. Now, vanadium has the atomic number of 23. So what I need to do is write out vanadium's electronic structure. So we can go 1s2, 2s2, 2p6, 3s2, 3p. And what's that? That's 10, that's 12, that's 3p6, that's 18. This is the same as argon. It's easy to do the shorthand argon. I've made that look like atomic mass. And so it has 4s2, 3d3. So 3 of the 3D subshells have only 1 electron in, so it also has 3 unpaired electrons. Let's check out iron. Now, iron has the atomic number of 26. So I'm just going to write AR, which is the shorthand for argon, the first 18, up to 3p6. That takes us. So then we've got 4s2. That's 20. I've got 6 more electrons after that to add in. So we've got 4s2, and then I go 3d6. So this means the 3d orbitals, I have 1 in each and then 1 that's paired up. That means there's 4 unpaired in the 3d subshell. There are 4 unpaired orbitals, so 4 unpaired electrons. So that might be the answer. Copper now has 29 electrons because its atomic number is 20. So I'm going to write the argon shorthand. I keep writing AR like relative atomic mass. That's a bit dumb. So it's going to have 4s2 3d9. However, it does this funky thing where it's better to not have a partially filled 3D subshell. So it has a full 3D subshell and half filled 4s subshell. So there's only 1 paired electron for copper. And that means that iron is our answer with 4 unpaired electrons. You know what they say. Sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks.
You're still here? It's over.